what I want to tell you guys about today is the slice filtration, and I thought it would be fun to kind of start with the origins and how we were thinking about things a while ago, where a while ago actually is like not that long ago, and then kind of show the progression and how we're thinking about things now and how exciting these new computations are that we're able to do. So if you know anything at all about the slice filtration, maybe you know that it was a tool that was instrumental in Hill, Hopkins, and Ravenel's solution to the covariant invariant 1 paper. So, okay, that's an exciting tool that maybe we'd like to study. And if you know one other thing about it, maybe you know that it's an equivariant analog of the Postnikov tower. So it's going to be this way that we could filter G spectra in some kind of homotopical sense. Okay. So if we're saying that it's this equivariant analog of the Postnikov tower, maybe the very, very basic idea is that we're going to take a G spectrum and we're going to kill maps from some kind of spheres of certain dimensions. And then keep track of what's going on. So when I say spheres here, what we're actually going to be killing maps from are things called slice cells, or other objects that are generated from them. But before I can give you the more precise definition of how this works, there's some notation that I'm going to go through. So throughout the talk, when I'm talking about a group G, I'm talking about a finite group G. And I might write H, and I just mean it's a subgroup of G. Sometimes G will be something specific that I'll try to be careful about pointing out, but if I just write G, it's just a finite group. Something that's going to be really important to us is the spheres that we're going to use. If we're thinking about things in the equivariant world, we might like to think about representation spheres. So if I write S upper V, what I mean is this is the one-point compactification of, well, the representation space associated to a representation V. Another thing I guess I'll throw up a whole lot is X. X is just going to be a genuine G spectrum. So when we're working with G spectra here, we're really working with genuine G spectra. And then lastly, there are going to be plenty of representation spheres that we might consider, but a really important representation that's going to get used a lot is the regular representation. So if I write rho sub G, I'm talking about the regular representation of G. Or in other words, the representation that comes from the group acting on itself by multiplication. All right, so I decided to start with maybe the first definition for general finite groups. In fact, this isn't the first time that, I guess what I should say is Hill, Hopkins, Ravenel is not the first time anyone looked at the slice filtration. Dan Duggar developed this for the group C2. But what I'll write up now is maybe the original definition for finite groups from the covariant invariant 1 paper. So I'll call this slice filtration classic. All right, so in order to tell you how we construct the slice filtration, we're first going to have to talk about what are these sorts of spheres, or what we're calling slice cells, that we're going to kill maps from. So here are some definitions. For group G, a slice cell is a cell of the form G plus smash over H for any subgroup H. with the representation sphere that comes from taking k copies of the regular representation for the subgroup H. And maybe we take a d suspension. So this epsilon is just 0 or 1. So when this was first being looked at, it was these kind of regular representation spheres, or 1D suspensions of them. And we want to kill maps from these to our G spectra in a coherent way. So it's not just these cells, but actually we're going to need collections of these that we can get some kind of localization functors associated to start killing our maps. So if we write tau sub greater than or equal to n, or I'll just say tau n, and I think maybe this is how Doug likes to do things now too, is just tau n's, but I'm still getting there, Doug. Okay. So these tau n's are localizing subcategories of G spectra generated by sliced cells of dimension greater than or equal to n. And when I say dimension here, I'm talking about the dimension of the underlying sphere. So that would be k times the order of the group H minus epsilon. So localizing subcategory, what are we doing? We're taking these sliced cells and then we're throwing in a bunch of other things. We're throwing in weak equivalences and retracts and wedges, and we're building up this subcategory. Just a note, if you are familiar with motivic slices, these are not triangulated categories, okay? But, you know, everything's in there that we need. Okay, oh, I guess I can put it over here. So associated to these categories, we have localization or nullification functors. So this p upper n minus 1 is the localization functor associated to tau n. So what we would say is if I took some G spectrum x and I applied this p n minus 1 to x, I'm killing the space of maps from these tau n's into my spectrum x. Okay. So what's nice then is that really these subcategories, they're all nested, right? It's just about the size of the dimension of the spheres. So say if I looked at tau n, that contains tau n plus 1, and so on. So what I have between these functors is natural transformations. So if I took a G spectrum x and I applied Pn, I have a map to applying Pn minus 1, and so on. And this collection of spectra that we've formed and the maps between them is what we call the sliced tower of x. Now, something that maybe we'd like to keep track of, I mean, right now maybe I haven't said a whole lot about what these objects are. We're killing maps, and as we work our way up the tower, it's like we're killing more things. Or I guess I should say, maybe the other way makes more sense, right? As we work our way down, we're killing maps from lower and lower dimension cells. But what may be something that you'd like to keep track of is kind of what's changing between each of these stages. That's a nice feature you might like to keep track of. And those fibers that I'll write P upper n lower n of x are what we call the n slices of x. So whenever someone is talking about the slices of a G spectrum, they're talking about these fibers in the tower. Okay, so maybe some remarks, some properties. I do have maps. I mean, when I apply this functor, what I get is a map from my spectrum to that functor applied to my spectrum. So just like in the Postnikov setting, I have a map from X into every section of this tower. And you might wonder about, like, you know, I've been a little bit vague. Like, these might look a little crazy, and then I'm generating other stuff, like what's really inside of here. Well, if I wanted to think about what those sections actually are, and I start kind of trying to identify objects that are in here, I might notice things like, well, if I took a trivial subgroup, I've got some trivial spheres in there, so that's going to affect homotopy in a way that I'd expect. All the way up to, if I took H to be the group G, then I'm just going to have a regular representation sphere, and that might, you know, give me something else that I end up killing. But in any case, there's some amount of control about the connectivity and the co-connectivity of the things in tau n. And so it turns out that just like in the Postnikov tower, if I were to work my way all the way up, I actually do get, I should write it like this, that the map from X to the limit of this tower is an equivalence. And if I work all the way down, I'm essentially killing everything. The co-limit is contractible. Okay, so that's looking a little bit like a filtration that we'd like, right? We're actually building X. Another thing, though, is kind of the equivariance. So I haven't really maybe said that much about why this is the equivariant analog. Obviously, we're using equivariant cells, but what's nice is we're using cells for all subgroups. So keeping in spirit with, you know, equivariant setting, we want to keep track of what's happening for all subgroups. We are here. And if we do things like, oh, I compute the tower for some G spectrum, and then I restrict that down to H, that actually will recover the Postnikov tower of my spectrum X thought of as an H spectrum. So we have this full notion of equivariance, and if we plugged the trivial group in for this H and just kind of, you know, forgot all of the action, we actually do recover the Postnikov tower. Okay. So maybe what I'd like to do before I you know, say more things about this in general is give some examples of kind of first things people noticed about the slice filtration. And maybe I'll highlight just some answers that people were able to come up with. So I mentioned at the very beginning that while this definition is in the Crevere paper, Dan Duggar, I guess maybe the thesis is in '99, well, he developed this for the group C2 and looked at real K theory. Okay, so then I guess it's kind of a gap until 2009. So what was actually looked at in this paper was the group C8, and I guess actually some of this computation, the computations really worked out for all cyclic 2 groups for complex cobordism, but maybe I'll say kind of normed up to being thought of as a G spectrum instead of just a C2 spectrum. So this was kind of, I mean, the useful part of the slice filtration was to understand more things about, you know, the homotopy here. And it turns out that the slices for this guy are actually, they're quite nice. Okay, so that ended up being kind of a key result. But I'd like to say just a couple other things that they worked out in this paper that are kind of enlightening about, what do we understand about slices. So maybe the first thing I'll mention that's more general than, okay, specific group, specific spectrum, is that for any finite group G and any spectrum X, we actually can compute the -1 and the 0 slices. Okay, so what are these guys? So the -1 slice, that would be that P -1 -1. And in our tower, so that's mapping into P -1 down to P -2. And so that's coming from, I guess, our tau, our tau 0 and our tau -1, right? And for low enough dimensions, it turns out that what these slice cells actually generate is just all -1 connected or all -2 connected G spectra, okay? So that means that we're killing maps from all things that are exactly as connected as we think they are. So the -1 slice is exactly what you would get for the -1 fiber of the Postnikov tower, which is just the -1 homotopy of your spectrum in dimension -1. So at first, it's like, oh, that's not really any different. But as you work your way up, you might find that these sorts of objects are not as connected as you think they are, maybe when you first look at them. So it turns out that for the 0 slice, it is actually an Eilenberg-MacLane spectrum, and it is giving you homotopy only in degree 0, but it's modified. So maybe, I've thrown up this notation. It's taking the homotopy in degree 0, and it's quotienting to make your restriction maps in the Mackey-Functor injections. Okay. Just maybe since I did not mention this, every time I underline things like this, I'm thinking about the Mackey-Functor valued object. Okay. But this is really awesome. So this is saying, like, okay, I know in any case I can compute my -1 and my 0 slices. And then, well, you might wonder, does this work for 1 and 2 and so on? Okay, things get pretty hairy. So maybe let's stop there about that. But if you did want to know about higher slices, what you might like to know is, these categories, they're governing what the PNs are doing. And if I could understand maybe that some of these categories were equivalent to other categories via certain suspensions, I could say something about, when these guys are giving similar answers, or when the slices come from lower slices. So turns out, since these are being generated by these kind of regular representation spheres, if I take slice cells and I suspend by a regular representation sphere, that's giving me an equivalence of tau n categories. So maybe I'll write it like this. SK rho G, if I smash with things in tau n, it will take me to things in tau n plus k times the order of my group. And this is an equivalence for all n. Okay? So what kind of thing does that tell us? That tells us things like, oh, if I know 0 slices and I suspend by the regular representation, then I know the size of my group slice and so on. So maybe I'll just put, for example, if G was C2, these two slices tell us everything because I can suspend by rho, which is dimension 2. So when G equals C2, all slices, maybe we'll say come from suspensions of -1 and 0 slices. Okay. So here's some stuff that we, I guess, know early on. But as I was saying, if we wanted to know, like if I picked a different group G, even if you looked at, C8, and you say, oh, could I use -1 and 0 slices to tell me about all other slices in C8? Okay, well maybe not, because I have to suspend by rho, and that would be dimension 8. So I'll make a couple more remarks in general, like maybe questions or things that one would want to know given this kind of information that we have so far. Okay, so I guess what we know so far is when n is -1 or 0, things are nice. And now we want to know about higher n. And the problem that I was alluding to earlier is that for objects in tau greater than or equal to n, this doesn't necessarily mean that they don't have homotopy groups below dimension n. So let's say this, x in tau greater than or equal to n are not necessarily n-connected. And actually, well, I guess I would have said n-1 connected. Let's say n-connective. Things will just be a little bit nicer. What I mean here is generated by these sorts of cells for dimensions bigger than or equal to n. Okay. So this is kind of, what's screwing with our understanding of what's happening in the tower, because as we work our way up and we're keeping track of these differences, when I form the next object, I might be affecting lower homotopy groups when I kill maps from these objects in tau n. Okay, so I'd like a nice way to keep track of this. So maybe question 1. How do objects in tau n, or how, maybe let's say this. How does, so if I say something is in tau greater than or equal to n, I'm saying something about its slice connectivity. So maybe how does slice connectivity relate to our kind of ordinary notion of connectivity? Okay. And I should say that even early on, in HHR, we do have some nice results that say, if I pick an object in tau n, I can say, actually, how connected that object is. What's a little tougher is to say, okay, what if I just pick an arbitrary object, and I wonder which tau n it's in, like which n? That's something that, at this stage, we didn't know. Okay. So what else does this mean? So as I was saying, that when we kill objects from these tau n's, we could be affecting lower homotopy groups. So our fibers, they don't necessarily, I mean, those two examples did, but if you suspend by regular representation spheres, maybe you get objects that have homotopy groups in lots of dimensions. So n slices are not always Eilenberg-MacLane. They're just not. So related to this, I said that suspending by regular representation spheres is nice, and it gives us these equivalences, and it lets us take slices that we understand and shift to understand other ones. We can't do that with trivial spheres. So when I'm saying these fibers aren't Eilenberg-MacLane, I can't shift by trivial spheres. So let's say if I were to do something like SK, I shift by K. This does not give us an equivalence of these tau n categories. Okay, but I've given you an example of some sort of suspension that does give an equivalence and some sort of suspension that doesn't. Are there some other ones that do? So here's a second question that I'll answer for you later. Are there other SVs that do give equivalences? Okay. There are lots and lots of other questions that could be asked, but I'm asking, too, that I will be able to answer for you later. Okay. So before I get to answering those, there's still, until we were able to answer some of those questions, there's still a lot of other work that happened since the Crevere paper. So I'd like to highlight some of that and maybe give you an idea, a little more about what we understand and what's just kind of mystifying. So after working with the slice filtration for the Crevere paper, Mike Hill put out a really nice paper that I think is, if you're trying to learn about the slice filtration, it's very readable, the equivariant slice primer. Kind of summarized some of the things that they were doing in that paper, and then also added on some new things that he worked out. So there's a lot of good stuff in there, but maybe I'll just mention a couple things. So one thing that I said earlier was, if I took some arbitrary G spectrum X and I wondered which tau n category might he live in, well, it's kind of a tough question, but initially Mike gave some conditions. So maybe I'll say some conditions for determining when an object was in one of these categories. Okay. It was really neat, but now they're maybe a little bit tedious and outdated. Yeah, no, they were really nice. I used those initially, but maybe we'll give you some better ones later. Another thing that was worked out that was really nice, so something that notice here is that we said, okay, we could figure out any zero slice, and it came from taking a quotient of a homotopy group. So I can't just put in any Mackey functor I want here and have that be a zero slice. So something nice that he worked out is if you took the group G to be a cyclic P group, when I write CP, I mean P is an odd prime. He worked out all the slices for Eilenberg-MacLane spectra. This kind of blew my mind, I think, a little bit early on, just because I thought, oh, you know, when we're talking about homotopy theory, Eilenberg-MacLane spectra, there's like nothing going on there, homotopically speaking. There's just one homotopy group, but there can be many slices. So very interesting. Another thing I wanted to highlight was also in this paper. He worked out the slices of what he called geometric spectra. So I'll say here that a geometric spectrum is just a spectrum whose homotopy groups, so they're Mackey functors, but they're concentrated on G mod G. It just only has homotopy coming from the G fixed points and nothing coming from the underlying stuff. And it turned out that if you only have homotopy coming from your G fixed points and nothing underneath, what your slice tower looked like was a re-indexed Postnikov tower. And I'll say a little bit more precisely about this later. But you know, maybe what this should be telling us is of course, something that we should expect is how important the fixed points are going to be for understanding what the slice tower looks like. And if we only have G fixed points, maybe it's saying, oh, it's quite simple. But if you have lots of other fixed points on subgroups, you have more interesting things going on in the slice tower. OK. So shortly after this, John Ullman gave an alternative description of the slice tower. So when I first wrote up what slice cells were, I said, OK, these slice cells, they look like these induced regular representation spheres or 1D suspensions of those. It turns out that if you ignore the D suspensions and you just use regular slice cells, or in other words, if you just always make your epsilon equal to 0, and you do the exact same game where you generate those tau n categories and you form the tower, you actually will get really the same information out. It just ends up being shifted by 1. So, you know, I guess working with these, a little bit nicer, and in maybe something, I don't know, that you might have thought about was if you were to try to multiply cells together and both your cells were 1D suspensions and now you've got a 2D suspension and it's not a slice cell anymore, that might be a little frustrating. But now the regular slice filtration will have nice multiplicative properties. OK, so from here on out, I guess most of what I'll say is using the regular slice filtration. But as I was saying, it really recovers the same information. So maybe let's say this. The same as slice filtration classic, but with a global shift by 1. And I think maybe the best way I can just indicate to you how that's working is to just, as an example, say, OK, so slice filtration classic, we knew -1 and 0 slices. When we're thinking about the regular slice filtration, we'll know 0 and 1 slices. And the 0 slices, then, are just those Postnikov layers, and the 1 slices will be those guys that come from taking a quotient. Okay, so just for example, that's how things are changing. So let me point out just a couple more results from Ullman's work that end up being kind of nice. So something that using the regular slice filtration he was able to work out was, okay, you know, these Eilenberg-MacLane spectra were worked out for cyclic p groups, and he worked them out for all finite groups. But of course, maybe I should say that they're just shifted, right? Because now it's the regular slice filtration. Okay. And another thing that he was able to work out, so now we know 0 slices and 1 slices, and he was able to work out -1 slices. Okay, so now we've got even more at our disposal to use, maybe shifting with regular representations to try to compute more things. But this would maybe make you think even more. Like, I'd like more suspensions by non-regular representation spheres to try to take advantage of knowing these sorts of slices to compute other ones. I will also maybe just point out a couple more slice towers that were computed, just to give an idea of maybe what's still confusing. So my dissertation, so 2013, but I guess it didn't appear until this year. Gives the slice towers for trivial suspensions of the Eilenberg-MacLane spectrum for the constant Mackey functor. And then around the same time, Hill, Hopkins, and Ravenel worked with the same group, but a slightly different spectrum. So this one's obviously, we're talking about trivial spheres. This lambda is going to be a CP to the k representation, and it comes from including the p to the kth roots of unity in the circle. So up top is something that's totally fixed in terms of g action, and what's on bottom is something that's totally free. Okay, so we worked out the slice towers of these two objects, and it's really interesting that, you know, okay, it turns out that, you know, there's a below, this object itself is already something that's in tau n. So the slice tower that you see for that starts in dimension n and then goes up and up and up until you can build the whole object. This is something that's, you know, like oppositely connected, and it turns out that this is something less than or equal to 2n. And I guess maybe this is misleading because I have n and 2n, but in any case, it's saying that for trivial things, we're seeing stuff above the dimension, and for this free object, we're just seeing things below the dimension. Okay, why? I don't know. It's a little confusing. Actually, I think maybe Ming Kong has some ideas about how these things fit together. Yes, so we're talking about the representation that comes from the inclusion of the p to the kth roots of unity in the circle. Yeah, so I'm talking about, I know there's lots of lambdas, I'm talking about the freest lambda. So something else that was kind of interesting in these is, what dimensions we were seeing slices in. A lot of times it is, multiples of p, or p to some power, and not a lot of changes in between. So that is also kind of, for the geometric spectra, it was this kind of re-indexed Postnikov tower, and it ends up being re-indexed by multiples of the size of the group. Maybe it's not too surprising that the sorts of slices we see are all things that are divisors of the size of the group. Okay. But in any case, I think these are nice computations, but it's still, it shows this kind of smearing out of homotopy groups, but like, in what way, or what information is this giving us? It's still, at that point, still very, very mysterious. Okay, so I want to, maybe the question from a lot of these is, can we describe more general slices, and what homotopy information is really getting filtered through? Like when I look at the slice filtration, how is that related to the homotopy groups of my spectrum? Okay. So more recent results, so by recent, I mean things happening in this year. Well, recall that result of Mike's I was mentioning earlier about geometric spectra. So maybe let's say for a geometric spectrum X, it turned out that the slices only occur in multiple of the order of the group. All the other ones are trivial. And they're just row suspensions of the homotopy groups of X. Okay. So when we're talking about equivariant homotopy groups, of course, we're talking about homotopy groups of fixed points. And I mentioned that when I'm saying geometric spectrum, I'm thinking about one that has homotopy groups concentrated on G mod G. So it's saying I've got homotopy groups coming from the G fixed points. Okay, so what this is maybe suggesting is that we could figure out slices, or we could figure out what things are in tau n's by looking at fixed points. Okay. For geometric spectra, because they're concentrated, their homotopy groups are concentrated on G mod G, their fixed points are the same as their geometric fixed points. Okay. And so it turns out that there's a really nice way to describe what things are in tau greater than or equal to n in terms of geometric fixed points. Okay. So this would be, maybe I'll say this, the answer to question 1 something is in tau greater than or equal to n if and only if its h geometric fixed points is n over the size of h connective for all subgroups H. So maybe we can see too by this, this thing being scaled out by these n times order of G, it was saying that the geometric fixed points needed to be n over the order of G connective. Okay, so this is really great, and this works for all n also. And it's particularly nice for things like representation spheres, Now we can say exactly when representation spheres are in tau n, because their geometric fixed points are just, you know, the sphere raised to the fixed points of v. So maybe I could say this. If and only if the dimension of the h fixed points of our representation are greater than or equal to n over the size of h. Okay, so that's something really nice. And this should also give us maybe a clue about when suspending by representations is going to produce equivalences of tau n's. So maybe this will be the answer to question 2. If v for, maybe let's say this, for any g representation v, smashing with SV will produce an equivalence from tau n to tau n plus k if and only if, when we look at the dimension of the h fixed points of v and add those to n over the size of h, if this is actually n plus k over the size of h, we have to use ceilings to make things work out. Okay, so anytime you can identify a representation sphere whose representation satisfies this for all subgroups H, then you know that what you have is going to produce an equivalence. Okay, so maybe I'll just say, you know, like why is this useful, or what could you compute from this? So some results from these theorems. Well, maybe if you pick particular groups G and you start looking at different representations, you might be able to find nice classes of things that will produce large numbers of equivalences. So if G is Cp to the K, Doug had a really clever family of representations that ended up giving lots of equivalences. So maybe we'll say this, when G is Cp to the K, it turns out that you can use that family of representations to come up with enough equivalences to sort the tau n's into 2 to the K different equivalence classes. So there's enough equivalences going on that we can identify lots and lots of our tau n's and move between them nicely. That doesn't give us immediately equivalences of slices, right? Slices are measuring differences between two things, so we'd need some successive equivalences of tau n's in order to get actual equivalences of slices. But in some cases, it's really nice. Like if G is Cp, it turns out that you have enough equivalences that those 3 different types of slices I mentioned before, the -1, 0, and 1 slices, are enough with suspensions to produce all the slices. And again, that p is for an odd prime. So it's really nice because it's saying it doesn't matter how big this prime is that you take, you really only need information about 3 different sorts of slices to come up with information about all of the slices. Okay. So that's a great question. So I know you're thinking like this 2 to the k, if I plug in 1, I'm saying that's only 2 equivalence classes of slices, but in terms of having the successive tau n's be equivalent to get the slices we want. So like maybe think about it this way, that for p equals 3, you have 0 slices or 0 taus are the same as 2 taus, and 0 taus are the same as, or tau zeros are the same as tau 3s, but tau 1s are not the same, so you can't get the equivalences of slices. Yeah, write that down, and I think you can figure it out, or we can talk afterwards. Okay, so this is like very super exciting that you could get all these slices kind of directly. And I'd maybe just like to highlight some other exciting things that people are doing. Okay. Oh, I'll just push this up. So I don't know, maybe I should say, also in terms of like recent work that happened this year, Dylan Wilson did something cool in using the slice filtration. Is Dylan here? Okay, well, Dylan Wilson did something cool with the slice filtration. You should ask him about it. So maybe I'll just mention, I guess, some work in progress. That's pretty exciting. So I mentioned that, right, getting equivalence classes of tau n's is not the same as getting equivalences of slices. There's a little bit to work out there. So, how will these equivalence classes give us equivalences of slices? Okay, Mingkong Zheng says, he's got maybe a working argument, we'll say, for how many slices these equivalences of taus will give. Sorry? There's no H? Oh, I'm so sorry, Mingkong. There's no H? Oh, man. I sincerely apologize. Okay. But this is right? This is, yeah, okay. Okay, so that's really, really neat. And another thing, so he's been working with cyclic P groups to look at. So I guess for my dissertation, I looked at just the trivial suspensions, and I have to be really honest. Like I thought that was really, really challenging. So he's been looking at more general representations, and so this is kind of saying something about like how much we've learned about how to be smart about performing computations. That at least for CP squared, he's got some idea of how this is going to work for general ROG graded things. And then one of Doug's other students, this also doesn't have an H, right, Jan? Okay. He has been working with D2P for odd primes P. And he's also looking at some very, very general representation spheres, SMET HZ, which is also, I mean, this is really impressive because at the very beginning, even just working with like CP was kind of tough. So this, at that time, I would have thought like, oh, there's no way, that's such a wacky group. I don't know how you would compute. So I think that's really, really cool. And then Bert Guillou and myself, we are looking at the Klein 4 group and some maybe slightly different spheres. And maybe, I think there's a very general. Right now, maybe Bert and I are looking at like some sign representations. And this is also, it's been really, really interesting. But yeah, I guess I'll go ahead and end with that and just say, and I'm sure maybe other people are working on other exciting things that I would love to talk with them about. So please come see me if you have other slice things that you're thinking about. Okay, thanks you guys.